Welcome to week 6 of the course, and this is the start of the second part of Math 213. We've been talking about differential equations up to now. From now on, we'll be talking about signals and systems. In a sense, it's a different way to look at the same material. So let's suppose that we have a differential equation. And think of it as a linear constant coefficient differential equation. And for simplicity, let's just say that all of the initial conditions are zero valued. So any conditions that you might want to specify, such as y of 0 minus, y dot of 0 minus, whatever, they're all equal to 0. What we've been looking at so far are essentially analysis problems, because the way differential equations problems are typically set up is that you're given a forcing function, f of t, and you're asked to solve for y of t. So in an engineering application, f of t might be what we are going to be calling from now on an input to a system, and y of t a response. So maybe, for instance, f of t represents the positions of the controls of a vehicle as time goes by, and y of t is the resulting trajectory of the vehicle. So this kind of question asks, well, if we manipulate the steering wheel in this way and the accelerator in this way, what will be the trajectory of the vehicle? But in engineering, we're often interested in what is essentially an inverse problem, an inverse of that problem, which we might call synthesis. And here we might say, suppose we have y of t, or some reasonable idea of what we would like the response y of t to look like. Find an f of t such that this y of t solves the diffie-q. That may not look all that different, but if you think of the vehicle, here the idea is we know more or less what trajectory we want the vehicle to follow. The question is, how do you manipulate the controls of the vehicle in order to make the vehicle follow that trajectory? That's more of an engineering problem. And that's the kind of problem that a signals and systems approach will let you solve. We might not know exactly what trajectory we want y of t to follow, but the idea is we know more or less what y of t should look like. We've got a reasonable idea, and the question is, does there exist an input f of t that will generate an acceptable y of t for us? That's the sense in which we're talking about an inverse of the analysis problem. So this is more complicated, and this requires an understanding of the relationship between these two functions, or what we're going to call from now on these two signals. So instead of focusing on solving the differential equation, we're going to focus on developing an understanding of the relationship between f of t and y of t. We're going to call f of t the input of the system, and y of t the output. And for a particular value of the input to the system, the corresponding output is going to be the response of the system. So you could say we're going to work at developing an understanding of the response of the system, the way it responds to a whole range of inputs, rather than just a particular one that we're given. So that, roughly speaking, is the difference in emphasis between differential equations and signals and systems. And to begin with, we're just going to define what we mean by signals and systems. So a signal is really just going to be a function of some independent variable t. And we're going to allow for this signal to be either real or complex valued. So for generality here, maybe I'll just write a complex valued function of an independent variable t. And t itself will be real valued. Now, normally, as the notation suggests, t will represent time. And there are two main types of signals of this sort. We talk about continuous time signals and discrete time signals. So if the domain of our function is the real line, the entire real line, say, or some interval of it, then we say that the signal is a continuous time signal. And we are going to be considering mainly continuous time signals. On the other hand, if the domain of the function is, say, the integers, or some other discrete set, discrete subset of R, then we say that our signal is a discrete time signal, or dt for short. So what would some examples be? Well, examples of continuous time signals would be essentially examples like we've already been looking at. Physical quantities are often, for engineering purposes, modeled as quantities that evolve continuously in time. So voltages, currents, displacements, forces, and so on. And we are going to concentrate mainly on continuous time signals, but discrete time ones arise in many applications. For instance, in economic or financial applications, one often uses a discrete time model. In an economic application, for instance, you might only have quarterly data. Or, for instance, if you're modeling, say, a computer, digital hardware driven by a clock, say synchronous digital hardware, clock driven. It will evolve at regular intervals, so you might use the integers, for instance, to represent the respective points in time at which things happen. Now again, we're going to focus on continuous time signals in this course. The first assignment was meant to illustrate that what we were going to learn about differential equations could carry over to difference equations. And the same is true here. We're going to do continuous time signals in systems, but everything we will do will carry over to discrete time signals in systems. In some ways, the continuous time is slightly more technical, perhaps, but also there are some complications that arise in the discrete time framework that we will avoid by using the continuous time approach. So generally, all in all, it's simpler to do the continuous time version first. And the continuous time version is particularly useful for a lot of engineering applications, such as automatic control and communications. In automatic control, we're often actually working with a system that has both continuous time signals and discrete time signals, because we use digital computers to control analog systems. But generally, the way we design such control systems is first to design an analog controller and then to approximate it with a digital computer. So initially, we assume that all of the signals involved are going to be continuous time signals. And it just turns out that things work out to be simpler that way. So in SE380, for instance, you'll learn how to design analog controllers, but you'll probably learn a thing or two about what to do once you've designed that controller and you want to implement it using a digital computer. So briefly, that's what signals are. They're functions of this independent variable t, which is real valued. They can be either discrete time or continuous time. We're going to focus mainly on continuous time signals. What is a system? Well, the mathematical definition of a system is that of a map from some space of input signals to a space of output signals. So in engineering terms, again, if you're thinking about the control of a vehicle, the input signals might give you the positions of the various controls as a function of time. The output signals would give you perhaps the position of the vehicle or its speed as a function of time. We will use different kinds of notation to represent systems. If script f is our space of input signals and script y is our space of output signals, then we can say that S maps from f to y in this way. Because these output and input signals are functions of time, we can alternatively say that y of t is what you get when you apply S to a function f. And when you do so, that gives you another function of t, namely y. So we could write y of t equals sf of t, and this is essentially because y is equal to sf. So we can also drop the t and just say that when you apply the map S to the input signal little f, you get the output signal y. And when we do this, what we mean is that y of t is what we call the response of the system to the input f. So if we apply a different accelerator signal to our car as a function of time, we want to see, say, what the resulting speed of the vehicle is as a function of time, and that resulting speed output, y of t, is the response of the system to our accelerator input, f of t. So that concludes the most basic definitions that we're going to use, those of signals and systems. Maybe I'll just make one very simple definition of continuous or discrete time systems. This distinction really just depends on the nature of the signals. So we say that a system S is continuous time, or CT, if, let's just say, its inputs and outputs are continuous time signals. In other words, if the input space and the output space are continuous time signals. And similarly, it's discrete time if its signals are discrete time. As I said, sometimes we have systems that contain both kinds of signals. When we describe a computer-controlled system, often we have to deal with continuous time and discrete time signals, in which case we're working with some hybrid systems. So S is a hybrid system. If it contains both CT and DT signals. So that's just a little bit of additional terminology. We have a number of different properties of systems that we have to define. Let's do that in the next video. So I'll see you there.